Do you know how to do full screen? Shut down. Yeah, I think we are all set. So now we can change the slides. I will just introduce you first. Então, boa tarde a todos. Meu nome é Vitor Clemente, sou professor aqui do Departamento de Engenharia Elétrica. E a gente tem o prazer de receber os professores da Arizona State University, Matthew Peet. Ele vai fazer uma apresentação para nós. E depois a Julia Peet, do mesmo departamento, da mesma universidade. Eles são do departamento de aeroespacial. Por favor. Eu queria introduzir, né, os apresentadores. Vou falar em inglês aqui, né, tá? So we thank you very much for this talk, for staying here. University of Brazil, we were prize to receive you. So I'd like to introduce the first speaker, Matthew Peet from Arizona State University, Arizona. It's a very nice place. Not the race tower. The other stations are very good. So I'd like to introduce the speaker. Matthew Peet received the bachelor's degree in physics and aerospace engineering from University of Texas, Austin, in 1999, and the master and PhD degrees in aeronautics and astronautics from Stanford University, California, in 2001 and 2006, respectively. He was a postdoctoral fellow at UnB, Paris, France, from 2006 to 2008. He was an assistant professor of aerospace engineering at Illinois Institute of Technology, Chicago, from 2008 to 2012. Currently, he is an associate professor of aerospace engineering at Arizona State University, Arizona. Dr. Peet received a National Science Foundation Career Award in 2011. His research focused on developing complex optimization-based tools for the analysis and control of nonlinear ordinary equations, time delay systems, and partial differential equations. So he has many publications in those areas. So he's a word of reference in this field. So I'd like to thank Dr. Peet for your presence here.
All right. Thank you, Eduardo. Appreciate your hosting and the interest in the talk and topic. So this talk is mostly focused on PDEs, although there is some discussion of sorry, a little bit hoarse. We were up. Eduardo and I were up a little bit late last night, so I'll try to speak loudly. Sorry. So the topic is partial differential equations with a little bit of a time delay system flavor. What we are trying to do, along with this incomplete list of collaborators and co-authors, is to create a state space framework for representation, analysis, and control of partial differential equations attempting to mirror the success that the LMI and perhaps the Riccati equations framework has been has had for ordinary differential equations. That's our goal. So to motivate this and place it in context of those goals, let me have 2 slides, relatively short, on ODEs and state-space representation and LMIs for ODEs. This talk is sort of the fundamentals, the representation, the framework, the toolbox, the computational part. Yulia, who is also here, will be talking about application to simulation of fluids and that sort of thing. This is a little bit abstract and theoretical, so if I'm not explaining it well or I'm not enunciating well, please stop me and ask questions. It's fine. I'll just skip the last 10 slides or so. They'll be okay. We'll also, I think, have 10 minutes between the talks for discussion and questions and chatting, basically. If you want to get a coffee, that kind of thing. All right, so what are we trying to do? State-space representations. So when we teach, well, some of us teach, like some people will teach, ordinary control systems, ordinary differential equations. We typically rely on one of 2 representations. We either use the state-space representation, which is a little bit more modern, or the transfer function representation. And the reason that we do that, of course, is that when we're teaching, we have no idea what problems the students will encounter once they leave and go into industry or what have you. And so we need to describe methods, techniques that work for any system, any representation, any particular application that they may encounter after they graduate. And so the advantage of state-space representations for ODEs and transfer functions as well is that any well-defined optimate or control or analysis problem can be specified using a combination of parameters, in this case matrices, or a transfer function if you're interested in transfer functions. So for example, if you're just interested in the dynamics, x dot equals ax, right? There's a matrix, an n by n matrix, which tells you everything you need to know about that set of dynamics. And so really, the only thing we need to work with is that A matrix when we're controlling or analyzing the ODE. Of course, for controls and estimation and various things, we augment that A with some other matrices. And that allows us to specify things we want to regulate, things we can actually measure, things which are going to perturb the system, and the things that we can actually control. Right? So we add these extra signals here, and then we go from 1 matrix to 9 matrices. But the point is not the number of matrices. The point is that these matrices tell us everything we need to know about that optimal control problem, even though we don't know anything about the application that we're going to come with. Any such application will have a set of 9 matrices which tell us everything we need to know. And then, of course, that would be fairly useless if we did have also computational methods, numerical approaches to using those matrices to find things like optimal controllers, estimators, do stability analysis. And we're focusing on LMIs, right? Generalization of LMIs as that computational tool, although Riccati equations is also a valid tool, which one could consider in this framework. And specifically, if you haven't encountered LMIs, they're just optimization problems subject to positive matrix constraints. So positivity of some matrix with an objective function and some constraints. And we have pretty good tools for solving these problems, the most common being Sadumi and Mosek, and very good tools for interfacing with those somewhat arcane tools in the form of UnB. But again, right, the point is that we have computational tools defined in terms of these 9 matrices. just I don't know if you can see these slides very well, but this is just an illustration of some of the things that we can do with those 9 matrices, particularly in the LMI framework. So stability analysis, this is an LMI, this is this Lyapunov inequality. This is the one for, this is the KYP lemma for H infinity gain, H2 gain. This is optimal estimation, optimal controller, state feedback controller synthesis. And sort of a common feature of all of these LMIs, I don't want to get into the specifics of them, is that they all inherently rely on some kind of energy or storage function, which is quadratic. So a Lyapunov function, if you want to call it that, which is important because quadratic Lyapunov functions can also be parameterized with a matrix, where now this is a decision variable. We don't know a priori what our matrix is going to be, our function. And all of these results inherently look for some such function. There's this one, there's this one, there's this one, there's this one. And then we do some manipulations and we get another quadratic function which we constrain in some other way to get an LMI. And the question is, can this framework, which is basically solved every possible problem we can think of with respect to analysis and control of ODEs, can that be extended to PDEs? I'm not even touching on the robust control stuff. Right. So that's the introduction. And then the question is, what is a PDE and can we replicate that success? So this is my introduction to PDEs. This is the collection of people who have sort of contributed to the representation of PDEs over time, or are responsible for how it currently looks. PDEs themselves, this is the simplest one we usually have, is the heat equation, the derivative in time, the double derivative in space. This thing has been around since these two guys. If you don't know them, this is Newton, this is Leibniz, and we can maybe even credit Euler over here. I don't know if you can recognize these other guys. Is this one? You know. The plus, that's the plus. This guy? Come on, I'll come to that guy. All right. So anyway, but this thing has been around since Newton started the whole differential equation thing back in the 1700s. Unfortunately, unlike ordinary differential equations, although it's been around, partial differential equations are a bit trickier to deal with than ordinary differential equations. Specifically, well, we can write down what we think of as the PDE, right? This is the PDE. We think of that as the PDE, right? And this is just a general way of like piling PDEs together so they're all coupled. So you can pretty much sort of ignore this thing. The problem with this like PDE is that it is vague. It defines a whole bunch of different solutions. So for any initial condition, the solution to this thing is not unique, not even close to unique. There are stable solutions, unstable solutions. This didn't receive too much attention because of these problems of uniqueness of solutions. You can't say much about it. It was only when we get to this guy, Dirichlet, in the 1800s, that we got what we think of as a unique solution. Like there's one solution to this PDE, and that was only through the imposition of boundary conditions. So that's some combination. He made B0, right? So he just set these two things to be 0, 0, 1, 0, right? This is the endpoint, and this is the end. So there's a spatial domain. So you just made both of those 0, and then there's a unique solution. That's what Dirichlet. Those are called the Dirichlet boundary conditions. We consider generalizations of this, any combination of these point values. The problem that unfortunately we think that you'd be done, but unfortunately not so much. So it's wasn't quite finished at this point. So we had a constraint, a PDE, but now we have a second constraint, which is the boundary conditions. And the question is that enough to define what we mean by a PDE? Well, we thought so for a while, but then this guy, Sergei Sobolev, came on. This is him looking old. He's actually very good looking. He's like when he was younger. He's like a little bit strange there. But Sergei Sobolev came along and he said, wait, now this isn't quite enough, because what is U of 0? What does that even mean? Doesn't that imply something about continuity of the solutions of the system? And it turns out that how you define that continuity actually changes how these boundary conditions change the solution of the PDE. So he added, in particular, that the spatial derivative has to be square integrable. That was like his contribution. Further constrain the solutions to lie in Sobolev space, which we call, of course, he didn't call it Sobolev. Maybe he did. So someone called it Sobolev space. Now we all call it Sobolev space. So that's an additional way in which we map. So this governs the way we map these boundary conditions as constraints on this solution to get a unique solution. So over, I think this is in the 1950s, over like 200 years of time, we started with the PDE, and we added the boundary conditions 100 years later, and then we added the way these actually interact only in the 1950s. Okay. And the way that they interact is actually significant, right? Because if you just think about Lyapunov functions, well, what's the derivative of that? It's this thing here, and right, the heat equation is very stable, but how does this, like, how do you enforce negativity of this? It's only by taking into account these constraints and sort of working through integration by parts or whatever you happen to be, that you can actually prove that the derivative here is negative. So a historical archaicism, if you will, that we have now 3 governing equations, all of which determine the solution. This is a problem because, of course, if we're defining computational tools, well, computers are not very good at sort of reconciling 3 conflicting sets of equations. And so our first goal then is to find a way to represent the PDE as a single equation, a unitary representation of the PDE. And so the question is, how do we get rid of those continuity constraints and boundary conditions? So if we just take the heat equation, just to illustrate that this may be possible, right? We can look at the heat equation, its boundary conditions, and figure out how they are related. So in particular, if we take this USS thing, we can actually relate, due to continuity, USS to U. And we write down, this is like Cauchy's rule for repeated integration. When we write down this equation, we can see the explicit relationship between USS, U, and the boundary conditions as they show up here. Of course, in this case, they're both 0, so this disappears. And we actually, if we take this expression, U equals this integral here, we plug it back into the equation, we get this term here, and on the right, we get this term. So a single equation then that we can use to describe these dynamics, all expressed in terms of USS. And you can do the same thing to the wave equation. You can write it as a single equation. Now, there are no spatial derivatives. Well, I mean, there's spatial derivative here. But the left and the right-hand side are the same thing. So this is an equation which describes the evolution of USS. The difference, of course, being there are no partial derivatives. Instead, there are these integral terms. This is integration from 0 to s minus theta being a kernel. These are integral operators. And we'll be doing a lot with integral operators. So that's significant. And the major distinction between the partial integral and the partial differential representations. We can do the same thing with the Lyapunov equation. We can also represent it using these integration operations. Okay. So this is just a general form of Lyapunov function. we now represent it as a L2 inner product of U and U with this integration operation. We can then take the derivative of it using those same relationships. Remember, U is expressed in terms of USS. So we write down the Lyapunov function. We take its derivative, so U becomes U dot. We then plug in U dot equals USS. Right? And then, well, we still have U on the other side, so we plug in for U in terms of USS as well. And we get that the derivative of the Lyapunov function is expressed entirely in terms of USS. And then this is an integral operator, which we can take its adjoint and move it to the other side. And I won't tell you how this happens, but we can express the whole thing in terms of USS and an integral operator on USS. Here are defined 0 to s and s to 1. So a single integral operator, well, or maybe two, depending on how you think of it, acting on that second spatial derivative. So we can express the dynamics, and we can express the Lyapunov function, and we can express its derivative, all using these class of integral operators. So that sets the framework for what we're trying to do. Right. But we're not quite there yet. Right. That's just motivation that this isn't possible in general. The key steps, of course, that we want to replicate if we're doing state space and LMIs, although we could do Riccati equations, is the key steps that are required for state space of ODEs. Specifically, we need to be able to represent any PDE in terms of a universal representation, universal form. We want to be able to parameterize the Lyapunov functions using a quadratic form. Just like matrices give us quadratic Lyapunov functions, and positivity of that matrix is necessary and sufficient for positivity of the Lyapunov function. And finally, if we're looking at stability and other things as well later on, the derivative of the Lyapunov function, when you plug in x dot, right, is defined in terms of this matrix A in the representation, P in the Lyapunov function, and that the composition of those also yields a matrix, which we can test positivity or negativity of. Specifically, the key properties are universality, the Lyapunov functions can be parameterized, and matrices critically form an algebra. They're closed under addition and composition. So if we want to do the same thing for PDEs, we want a state space representation, we need some way, and it's going to be defined in terms of integral operators, to replace these steps with operators. Matrices go to operators. They have to be able to represent a large class of PDEs, preferably any PDEs. They have to be able to parameterize the Lyapunov functions, and they have to form an algebra. And of course, in the end, we need a computational tool for optimization of those operators. Operators, you can just think of it as a form of matrix. So the new matrix, if you will, that we're defining for PDEs is the algebra of partial integral operators. So what is an operator, right? An operator is, what is that different? A matrix is an operator. It's just the problem is our state for a PDE is a function space, whereas the state for an ODE is a vector, right? Your initial condition is a vector here, and your initial condition is a distribution of the state over a spatial domain in the case of PDEs. But we can think of operators as matrices, just acting on a really large vector, right? So for example, if you take like every point in this domain, or a set of them, right, you can write down a vector and think of the operators acting on those specific points, just to get intuition. So if we think of, there's two classes of obvious operators that we consider the multiplier and the integral operators. The multiplier operators are like transfer functions, right? They multiply in H2, right? A function, and just multiply at every point in S by that multiplier. Right? So the multiplier corresponding to P is this thing. But if we think of that as a matrix, well, this is a very restrictive class of operators. We only have transfer functions for linear, causal, time, and variant systems. And so if we write down the matrix equivalent, infinite matrix equivalent of this multiplier operator, it's simply a diagonal matrix. And we really can't do much with diagonal matrices. So multiplier operators, very simple, but not particularly useful. By contrast, integral operators are more akin, similar to what we think of as traditional matrices. So each of those points in the spatial domain defines one of the elements of the matrix. So Kij is Si theta I. And then this kernel is what we call it. It's integration of this second here spatial domain with here. And then there's the K has an S thing there in front of it. So if you replace summation with integration, then you get that the infinite matrix equivalent of this is just the matrix whose elements are those spatial points. So it's a full rank matrix operation. And I don't want to get into properties of operators. So I'll just focus on one particular property of operators, which is in terms of those kernel functions. This is like perhaps a little more theoretical aspect, but it's important because for in infinite dimensions, little subtleties like this actually make a big difference. So in particular, if we think, say, took the obvious choice of how to represent these kernels and we made them polynomials, which is the easiest thing we have to parameterize, well, that's a problem because polynomials are separable. So if you think of like how to solve PDEs, we usually assume that solutions are separable. This is not good when applied to kernels. Because if we take the infinite matrix equivalent of this kernel, it is a vector times a vector. And this, so you think of this as F and F transpose. So the outer product of two vectors. And we know that the outer product of two vectors is rank 1. So if we consider only polynomial kernels, we're only going to have rank 1 operators, which is like not going to be useful in representing anything. The alternative, though, is actually almost identical, but the almost is there's a big gap between identical and almost identical. So if we instead define this kernel using polynomials or separable functions above and below the diagonal of that matrix, right? Think of this as a matrix, right? Above and below the diagonal, right? Then the operator, the form of this infinite matrix changes drastically. So it defines a diagonal matrix times a lower triangular matrix, both of which have full rank. So the correct or the more useful version of kernel is one which is we have polynomials above and below the diagonal elements. And then we get full rank operators, and we can use it to represent all sorts of things. So that is, in fact, actually exactly what we define the class of partial integral operators to be. So the lower triangular part, the upper triangular part, and then we throw in a multiplier for good measure because we sometimes need it. But mostly the important part are these two kernels, the upper triangular and the lower triangular parts. So this is a set of operators. All such operators with polynomial factors R1, R0, and R2. So if you define this to be a set, and define a composition operation on these operators, you can show that this is closed under, it's in algebra. It's closed under composition, addition, adjoint. Has all the basic properties of a matrix algebra. Concatenation, everything that you could define for matrices almost is defined for this class of operators. So this is what we define as the 3 pi operators, because there's 3 parameters. It's a map from L2 back to L2, function space to the function space. And sometimes we need to couple ODEs to the PDEs. And so we expand it slightly to allow maps from real numbers to real numbers, from function spaces to real numbers, from real numbers to function spaces, and then of course function spaces to function spaces. So this is a slightly more general form, which is needed for, say, time delay systems and coupling with ODEs. But we don't need to dwell on it. So now we have a class, an algebra of partial integral operators. And the next question is, how should we represent PDEs using those operators in lieu of matrices? So, as hinted at earlier, right, the first step is to redefine your state. So instead of defining the state of your PDE as given to you, as u, we redefine the state of a partial integral equation as the highest order spatial derivative as allowed by the continuity constraints given to us by Sobolev. So this is just a stack of like coupled states. So just like the highest order derivative of each, you can ignore the other parts, just focus on the last one. So we have the original state of the PDE, and then the pi state is the highest order spatial derivative of that PDE state. The big difference, of course, is that the PDE state has boundary conditions. So we have a set of boundary conditions which are imposed on the PDE state, but the pi state does not require to satisfy any of that. So if we define our dynamics on this pi state, then we can use these computational tools for analysis there, and then hopefully be able to map those results back to the original PDE state. You can think of this as a similarity transform, the way we have controllable canonical forms and observable canonical forms for ODEs. This is a very simple version of how this works, but most of it is encoded into the software at this point. But I'll just go through it briefly. The first step is find the relationship between the highest order spatial derivative and the initial state, which is then expressed in terms of left boundary values through Cauchy's rule for repeated integration, or actually generalization of that. We then are not given these left boundary values. This is on the left, A is on the left. We're given this set of boundary values, these boundary conditions. But if we plug those boundary values into this equation, we get a relationship between both of these things and this guy here. We can then solve for both boundary values in terms of that state, then plug that back in for our left boundary values, and we can universally find a representation of this original state in terms of the highest order spatial derivative. So in terms of a phi operator, there always exists for any well-posed PDE on a hyper rectangle, such a pi operator, T, which relates the highest order spatial derivative to the original PDE state. And this is just a universal way of constructing that. So now we've got two representations. The original PDE, which is defined in terms of differential operators in the original state, where the state is constrained by boundary conditions. And the PDE pi, where we take that original state, we plug in for xf, that highest order derivative, x equals tf. We plug x equals tf in here. And then it turns out the composition of these differential and Dirac operators with that t are always, again, of that partial integral algebra. They always have partial integral representations. That's how they're precisely defined. I won't go through the details of why that's true, but it is. And then these two systems you can show have equivalent properties in terms of a solution to one. That one gives you a solution to the PDE. If you solve the pi, you can get a solution to the PDE. If you can solve the PDE, you can get a solution to the pi. And if the PDE state goes to 0, so does the pi state, or the stability properties are equivalent. As are the L2 gain. I don't know why this equation is here. Ignore it, please. So now we have a representation, a universal representation of PDEs in terms of partial integral equations. This extends to multiple spatial domains. Recently, it's been extended to nonlinear systems, periodic boundary conditions, all sorts of things. Inputs and outputs, forcing functions at the boundary, all sorts of such problems. And the question is, can we define now a computational tool on this representation using those parameters? And that's the sort of final part of the talk here. Although I'm only on slide 14. The last 20 slides are just like illustrations. So the basic approach is to take those quadratic Lyapunov functions we know and love for ODEs and put them in the PDE framework, and then replace that PDE state with the pi state. So that when we take the derivative, right, we have this normal ODE quadratic Lyapunov function derivative. We replace that with these differential operators, and then we multiply those derivative operators with that TXF thing. So that these now become partial integral equations. And now the obvious stability criterion is if this operator is positive, the Lyapunov function is positive, and if this operator is negative, the derivative is also negative. So the real question then is, can we enforce operator inequalities where now these P's are going to be decision variables? We're going to have to search for these P's, just like we did for LMIs. We can extend this, that was just a stability, but we can extend it to controller synthesis, all sorts of things, because this algebraic structure allows you to do things like duality. So we know for ODEs what the dual system looks like. Its stability is equivalent. Controllability of the primal gives you observability of the dual, and so forth. That all holds for pi's as well. Where now we take A goes to A star, that's adjoint in the inner product, L2 inner product space. B goes to C star, so instead of transpose, it's star. C goes to B star, and D goes to D star. Same as for ODEs. Only difference is we have this T and T star over there. And then stability of the primal and dual are equivalent in a sense, which I think I have a note on next. And the L2 gain, again, I don't know why I have this equation here. It's like extra. L2 gain is also equivalent. So H infinity norm is also equivalent of these systems. Controllability, H2 norm, all of those properties. Here I'm like making a technical note that stability in PDEs is a little bit nuanced, let's say. As in, stability of a PDE, as we think about it, is not always the correct notion. So for example, wave beam equations are not Lyapunov stable in the classical sense. So we have to define a slightly different notion of stability in terms of the output, the solution is a PD state, and the initial condition is defined in terms of the pi state. I can talk more about why that's true. And it's, of course, in the code, but I don't want to get into the details too much. So H infinity optimal control. You can represent that LMI that we had for ODEs as a LPI, where now the matrices are replaced with pi operators, which you can search over. There's a version for output feedback. Output feedback is a bit input at the boundary, control of the boundary is very tricky for PDEs. I don't know if you work with PDEs much. But the problem with control at the boundary is that the input doesn't appear in the PDE, right? You write down ut equals uxx, that write down the PDE, there's no input to it. So how do you control something with no input? I go all the way back, right? Say I have a control of the boundary, I can control the boundary value. This is a common problem in PDEs. If I just write down the PDEs without the boundary conditions, there's no input in it. It's only when you have these unitary representations that it actually becomes clear how the input affects the evolution of the PDE. And in particular, right, here when we write down the pi, right, the u actually appears in two places, u and its derivative. It introduces new problems with convexification in controller synthesis. I won't talk about this inequality. It's a sufficient one. These classes of boundary value problems, boundary inputs, are challenging. Sorry, there's my voice again. Nonetheless, right, we have all these LMIs for ODs: stability, duality, control, estimation, or H2 gain, and they all have an LPI equivalent. And so, of course, now our final problem becomes: can we test those LPIs? And the answer is, of course, yes. We have a software tool called PIETOOLS. It's been in development for about 5 years-ish. There was a 2020 version. It's now on version 2025, just came out 2 days ago, I believe. It has not been, the website has not been updated, but the GitHub link has been. So if you go to GitHub, you can actually download PIETOOLS 2025, which is, I suggest you don't use previous versions. There's a very long user manual, quick get started manual, and I think actually we don't have a new tutorial, but we used to as of 2020. But it's not this one. I don't think this will help you very much. So maybe we need to update that. We can put this lecture on as a YouTube tutorial. No, actually, it's a useful tutorial, just not up to date. So how is PIETOOL structured? The first step, and perhaps the most difficult in terms of getting it right, is representation, right? How to enter your PDE itself, right? And that's one we focus on a lot. How the user declares their PDE. The rest are a lot under. It's quite a bit is under the hood. Once you've declared your PDE, right, there's a converter which will give you your pi representation. It's defined in terms of those pi parameters. Those are then used with you can define LPIs and solve them with LMIs. There are scripts for various common tasks. There's a simulator. So once you've declared it, I think you'll be talking about a little bit. There are computational methods for simulation of that PDE. And of course, you can combine them, right? You can find a controller gains, and then implement it in simulation, all within the software framework. At this point, and I'm just presenting the software, so there's no more theory. The core elements of PIETOOLS is the pi operator class. It's called the opvar class. It replaces the matrix. So anything you want to do with the matrix, you're used to doing with the matrix, you can do with an opvar, right? A pi operator. It's defined by those parameters, those polynomial parameters, but that's all under the hood, right? So if you have such an operator, they usually come from the converter. It has all of these parameters inside, but you don't have to manipulate them individually. In fact, if you did, I would feel very sorry for you because it's like integration by parts to no end. But this all is automated. There's analytic formulas for composition and all of these operations which are embedded in this opvar class. So you can do, just do A plus B, and you get another opvar, negative A. You can even do sub-referencing, concatenation, horizontal, vertical, whatever you're used to doing in MATLAB or Scilab or what, it's not in Scilab yet. If you were to do it in MATLAB, all of that is over-defined on these op bars. So that's the key element. To get the op bars, which represent the PD, right? This is the input framework as it exists as of 2024, also 2025, of course. So to declare an ODE variable, right, you just give it PD bar. It creates a symbolic object in the workspace with nothing, right? It's just a place. I mean, you can give it a dimension, but this creates a scalar ODE variable. It says nothing about it. If you wanted to create a distributed, like a PDE state, right, you have to give it a spatial variable and a domain. If you want to create an input, right, PD bar within, this is also an input in this case. So this is an ODE coupled with a PD. These are the, this is X, this is W. And then you define the equation. I should put actually, there should be brackets around this. You just differentiate it, right? Diff X with respect to T equals negative X plus U, just as you read it. Diff X with respect to T, that's this one, the big X, equals lambda, right? Just as you see it, that's how you write the equations. Of course, there's no boundary conditions here because you also need to add boundary conditions, but we're not doing it here. And then you initialize. It'll tell you if you don't have boundary conditions. This will not work because it doesn't have boundary conditions. But if you did, right, you pop them in this pile of equations and push initialize, and it'll give you an ODE PD structure. There's also a GUI, but at this point, the command line interface is far superior, so I wouldn't use the GUI. Once you push initialize, it pops out a PDE, and then you just type convert, and it gives you a pi. And that pi is defined by these parameters. Right? All the possible parameters, and those are all op bars, which you can manipulate in the workspace. The reference is the elements of that structure, the pi structure. So if you want to define an LPI, right, you need these things in the workspace, and now they exist in the workspace. And then, of course, we need a way of solving these LPIs. And for that, we also have a toolbox. So we're just going to illustrate this with the controller synthesis LPI. There's three parts you need to declare. The decision variables, that will be P, gamma, which is the objective as well, and this indeterminate variable Z. Constraints, positivity and negativity constraints, and your objective. Right. So this is how you do it. Right. You declare a program structure, and then you add variables and constraints to it. So it goes in and it comes back out. This one creates a positive operator, P. There's some arguments to it, but it takes that variable and appends it to the program structure. So it doesn't have to be the same. I mean, you can like create prog2 or something, but it gets confusing, so I wouldn't do that. You can create an indeterminate variable, which we'll do for Z. You can add inequality and equality constraints. Again, passing prog back and forth. Adding this equals to 0, this greater than or equal to 0 here, and this is equal to 0 here. For equality and inequality. You can set an objective, right? Again, passing the prog structure back and forth, and now this is your objective. You can solve it with this command, right? You have to have an SDP solver, so MOSEC or your Sudumi, or any of the others, but you have to have one because it doesn't have its own LPI solver. And then you get the solution, and then maybe you want to simulate it, but I think Yulia is going to be talking about simulation, so I'm going to mostly skip this. Right? Okay. And then just a final demonstration of the complete set. Here's a PD. It's we got an ODE. We have a PD. This is a wave equation. second order in time, second order in space, with some terms over here, and then here's your boundary conditions. So what I did in this case is like I created two state variables phi and phi dot because it's second order. You don't need to do that. If you just enter phi double dots diff, if you enter diff x t comma 2, you can use second order derivatives as well. It's fine. So I didn't need to do that, but I did. So you have one phi and phi dot because I used the state space. Define some inputs, define your output. Here's your OD dynamics. Here's your PD dynamics. This relates phi dot to phi, right? So phi dot is the derivative of phi. And then there's our PDE. And then we have three boundary conditions here. It'll let you know if you don't have enough boundary conditions to be well posed, in which case you want to add another one. And then you have an output. And then it has a script for doing various things like stability, also getting support. And then this is just the workflow. Here we're simulating the open loop with Python, which we usually will talk about. This is again open loop. We design a controller with LPI solve here. Actually, I think these arguments are reversed. There's a way of constructing the controller by inversion. It's really very simple script. It's not very interesting. And then we can simulate the closed loop solution as well, right? Just here, using Python again for the closed loop as well. All right, so that brings us to the end. This is the framework, right? We have the user interface for declaring PDEs. Those are converted to those parameters in the representation. PIETOOLS 2025 is the latest version. It's available on GitHub. Conversion, all of this stuff that we've seen is very fast. The LPI is not so fast when you actually take it out to UnB. Depends on the size. There's various internal parameters, which of course I couldn't possibly talk about today, but they're all in the user manual. And so I think with that, I'm gonna stop, and we can I can answer questions and discuss anything you want to discuss. So thank you.
Okay, let's take this. I remember that our two talks, Professor Manuel, he talks about the theory and the methods how to deal with PDEs with a software tool to how to make analysis, simulation, control, estimators, state estimators, and all kind of stuff. And we have a next talk about applications. So if you are terrified that the applications are coming, and I'd like to open for questions. It can be not only about predators but things related with PDEs in general, stability, the equations. If someone wants to ask importance, we can translate as well. So I'd like to open it for questions and comments. I think most of us, I am included, are not so many familiar with PDEs. So I have some points because here that's we that are from OD family, I would say that in most undergraduate courses we learn Laplace transform. That's a very efficient tool especially for single input, single output system. So we're going to solve the ODE. You can have qualitative behavior look into the transfer function to the poles and zeros, etc. So the first ingenious questions is like, does it work as well for PDEs? Is a way of that we can deal with these as well. So that's a first question, not very related, but just to understand that. So I will state all questions, then I think you can explain that. And the next question is about stability, because when we have more complex system, even for PDEs, multiple inputs, multiple outputs, we have to move to steady-state equations. And then we are interested about the trajectories. If we think about stability, we think about trajectories conversion to origin, for instance. Then we define an energy function. Right? So instead of solving the system and computing the trajectories, we build an energy function. So we see if this energy function decreases. So we can state stability like this. So when we move to PDEs, there is first a question about the intuition of the stability, because now we have an infinite dimension. So it's like if we think like a segment with infinite points, we can think about like piecewise, pointwise, or in space, like each infinite point of this space conversion as a trajectory conversion to origin, for instance. Or we can think about the energy of this segment, this energy conversion to origin. So the question is, are there many ways of defining stability for PDEs? Like, what's the intuition for this? And finally,
I might like forget your question.
yeah. Okay. I'm gonna go point.
Okay, let me start
Okay.
with the trend, because I think like that's when I remember.
Yeah, okay, so that's a great question. So, right, what is our transfer function, right? Our transfer function is right, defined as the in the H2 space, right? That's the output over the input. So the question is, well, in ODEs we have I minus A inverse B D. We're from the state space representation. The question is, can you do that for PDEs? Let's consider something like UT equals USS. And then maybe we have, right, input at the boundary. Actually, I have too many U's. Maybe let me call this W. So that the boundary value of, here, I'll just put some time in there. So the boundary value of W is the input, right? So how would we get this? Well, I mean, obviously we need an output, YS. Let's just make that W. Or maybe it's the square integral of W or something like that. But the obvious problem is if we apply the Laplace transform to this equation, right? Well, I mean, the obvious problem is our input doesn't appear in there. That's the core fundamental problem. So how do we get a transfer function when there's no input, right? Transfer function is a relationship between the inputs and the outputs. And so in the classical PDE case, basically there are transfer functions for certain PDEs, but they essentially rely on solving the PDE, right? Getting an analytic expression. It's like extremely difficult. Then when you have an analytic expression, you can map the U input to the output. One of the nice things about pies is that, right, if you have T x dot equals A x plus the U, right, the U appears in the differential equation. So you can, right, apply the Laplace transform in terms of U. And so your transfer function for a pi would be something like C T S minus A inverse B plus D U, where these are pi operators now. Typically, we want this to be mapped to a real number and from a real number. So this would actually be real valued in most cases. But yeah, without that way of mapping the input to the output, there's no way of getting a final Laplace transform.
The great advantage is we are incorporating the information of the boundary conditions to the equation that represent the dynamics. So then we can apply, like we say, classical methods to analyze this PDE without being worried about extra information that's not coupled for instance, boundary condition. And the second point is like some intuition for stability of PDEs. As I said, for ODEs, we can think about trajectories converging to origin, for instance, and associating an energy function. For PDEs, we have this segment. So we could think in two different ways, like an infinite number of trajectories, each one for each point in the space, in this segment. Or we can think about the energy of this segment going to the origin. Or if there is another ways of regarding this problem of stability of
So that, that's thank you for asking. Very good question. The problem with stability of PDEs is really related to the norm, how you measure. All Euclidean norms are the same, right? I mean, if Rn, they're all equivalent up to a constant. In PDEs, it's not the case. So an obvious example, right, is the wave equation. It's like describes a wave moving from left to right. U double dot equals USS. Wave that. How do we measure the energy? How do we measure the decay of this system? So in ODEs, right, we would say the norm x of t is less than some constant times the decaying exponential times the norm of the initial condition. That's what this is. Notion of stability. You can have zero decay. I mean, you can just we can get rid of that entirely. But there's some k such that a finite size initial condition maps to a finite size output, the outcome stability. Equations like this, which are obviously, they're not decaying exponentially, but they're obviously neutrally stable, do not satisfy this unless you use the proper norm. So for example, there exists for the wave equation no k such that this is true if we're measuring here the L2 norm, right? The square integral, the obvious generalization of Euclidean norms to infinite dimensional space is not satisfied for something as simple as the wave equation. The reason is that an initial condition of this size, say this was your initial condition, right? That has the same energy as an initial condition which looks like this, vibrating very fast, which is obviously non-physical, right? This initial condition should not have the same size as this initial condition. But if you're just measuring the deflection of that wave, right, that's what this says. So you've got to define your initial states, your notions of stability in terms of the appropriate norm, and the appropriate norm is the one proposed by Sergey over there, which is the deflection, but also the spatial derivative of the deflection. Here, I'm like, there's a spatial domain. This is time equals 0. C equals 0. Okay. So L2 norm of the deflection, but also the flux of the initial condition factors into the norm. So this is like why we use the pi to PD stability to get this kind of notion of, to capture this kind of notion of stability, which are decaying. Heat equation is very stable typically, but these other notions, especially when you're doing controller synthesis, especially at the boundary, that it makes a big difference.
But when we are having, for instance, the heat equation, we use like the PIETOOls to convert this PDE to a pi representation, and then if we apply stability methods, what kind of metric are we using? The first one, that's just L2, or the Sobolev metric for that incorporate the deflection and the.
So as of 2025, we're using this one.
The blue one, okay.
Yeah.
Okay.
There is an option there's a different script you can run to get the first option, to get L2.
Okay.
If you're interested in that kind of but again, I don't recommend it because depending on how, within L2 norm, there are ways of defining the system, the dynamics in a way for which this is satisfied, but you have to sort of know what you're doing.
Okay.
So specifically, if you define the state as UT and US, right, then this is satisfied, but otherwise, you have to, it's not.
Okay. And now, up to now, we're dealing with linear PDEs. Any class of linear PDEs we can view, or there is some restrictions for the class of problems?
Well, the hypothesis is that any well-posed linear PDE can be represented as pi.
Okay.
There's like some things like periodic boundary conditions for which the notion of well-posedness is subtle. There is a test for well-posedness now in PIETOOls, so you can test well-posedness of the PDE, which is something that PDE people care about. Maybe engineers not so much, because we assume that whatever we write down is going to be true. But the PDE people care about it a lot. So there is a test, an LPI, to prove well-posedness of PDEs, and the pi, of course, as well.
But up to now, the user needs to make a verbal transformation if the profile is not the origin. I mean, the equilibrium points on the origin, right? Does the software do that, or these are this?
Yes,
We are, the mathematical framework assumes, I mean, the representation doesn't assume anything, right? You get to the pi representation, right? I mean, this doesn't assume
that W is 0, for example. I mean, it could be constant. Representation is still true. I mean, you could just let W be 1.
I mean,
this would still be valid.
But I mean, considering there is no input, Well, the boundary conditions are not zero, for instance.
Well, then you could put a boundary condition at the, right, you could create a fictitious signal, W, right? You just said,
Okay.
0 equals W T, but then just make this W T equals 1, right? I mean, okay, I mean, we call this like, a regulated output or whatever, because we're in the controls framework, but like, other people may not like that name, right? You just say some other boundary condition. It doesn't matter what it is. You could like let it be a step input. You could let it be whatever you want, and the representation is still valid. So it covers that case. It's just yeah. This is more general.
Okay.
Other questions?
Does anybody?
I have a question. My name is Ricardo. I'm from the mathematics department.
Okay. So you're a PD.
I do have a question. When one talk about the PDEs, the first question is what kind of solution are you interested for? Is it regular solutions or solver level solutions?
So typically we're interested in classical solutions, right? So
But since the approach looks like very wild, this can be mainly for any abstract space, I suppose.
yes,
Where you have the web model just the linear PDEs.
so I'll hedge what I said earlier in that, like, right, these represent these functions, right, are in L2, right? So they're not like, when we talk about solutions of a pi, we're talking about things which are not continuous, like, so they're not classical solutions in that case. So we talk about, weak solutions, right? We're talking about projecting onto an L2 space. We're already on an L2 space. So if these are well posted, the notions are equivalent, actually.
But one can think in some Linux space, nor L2, nor hybrid space, or, and the boundary condition can think about the trace sense, not continuity, or a little bit more general, because the frameworks look like very wide, very abstract one to be applied in Linux space setting, using, for example, for evolution equation, semi-groups view.
Yeah, so I mean, if it's our solutions are in L2, we prefer them not to be constrained. But for example, when we talk about periodic boundary conditions, we're usually looking for solutions on a subspace, for example. So that we occasionally consider subspaces of L2, but not usually arbitrary Banach spaces. So but that's something that would fit in the framework. I'm just trying to think of the example. Well, we can talk about. Are there any other questions?
Thank you for
Thank you.
about the initial conditions. You have mentioned that all initial conditions are embedded in the without condition. Without the I don't remember exactly. But in the pi equation, you have initial conditions. Some here you have initial condition. So you can incorporate some initial conditions or fundamental.
Yes. So the method actually says here.
You have it there, xf0 x0. So you have initial condition.
Yeah. So this is
So you have mentioned before that you can take all the boundary conditions and eliminate them. So you can choose which initial condition, boundary condition you eliminate, or which one you use as an initial condition.
Premise is we'd like to eliminate all of them, right? And so that we have no boundary conditions left over. So that there is a clean map from this function to this function without these auxiliary terms. If you would like to eliminate fewer boundary conditions, that becomes a little bit problematic because you may not have a clean map from this variable. You may not be able to invert the, basically when you plug in for these left and right boundary values, you may not be able to invert unless you have enough boundary conditions, basically. So you need like the number of boundary conditions has to be equal to the order of differentiation. If you have like u dot equals USS, right, you need 2 boundary conditions. If you only want to use one of them, then the map is not uniquely defined. And you can express it maybe in terms of like the other boundary value.
Perhaps by contracting contract and create some condition, some boundary conditions you are using as input.
Yeah, so
Some boundary conditions and also as initial condition for instance. For 0 is a boundary condition. Conditional
boundary in time or
yes, here you have the boundary conditions. And in Python you have the x 0.
So,
so
X 0. So do you have an initial condition in time?
yes, so
This initial condition is not initially a boundary condition.
no, this is a pi, it doesn't allow for boundary conditions.
Okay,
So that's that,
yeah.
But then when you plug it into, so this is the same function here,
Okay.
right? So when you plug it into the PDE, right, you operate it through this map, right? So this maps the initial pi state to the initial PDE state. So this is at every point in time, this is the map from pi to PDE state. So no matter what you choose for x naught, anything in L2, this will satisfy the boundary condition because it's embedded in this T operator.
good question.
Okay.
Okay.
Let's take the sticker again.
Thank you for your discussion. I'll let.
Okay.
Oh, sorry. Okay, it's here. So would you like to transfer or is there a USB?
Yeah, it's the same as yours.
Okay.
You want to get a coffee, I guess.
I mean, a break or something like that.
Coffee break?
Okay. Yeah.
Yeah. I have an extra Coke Zero.
I would have like a 5 minutes break. I just don't have.
Oh, you don't have coffee.
Break.
Where would I see?
Sim.
Like,
We can have like a
5 minutes break.
while we set the